In this video, I am going to walk you through just a couple of stoichiometry example problems, just some different types. Maybe you're given moles, maybe you're given grams, maybe the answer is asking for moles or asking for grams. The heart of the problem doesn't change. The heart of a stoichiometry problem is all about that mole to mole ratio, but sometimes the given could be in a different type of unit, or the answer being requested could be in a different type of unit. So what we're going to do is we're going to look at how do we handle that, and it's stuff that you already know how to do. It's really easy. You've just got to really think about what did they give me and what are they asking for. So I have already posted one video on this topic, and that's probably the best one to start with, but I am going to go back through the basic steps before we begin. So for a stoichiometry problem, the first thing we always have to start off with is a balanced equation. Sometimes you get really lucky and you'll have a problem where you are just given a balanced equation, and sometimes you're held to a little bit of a higher standard. Maybe the problem's wanting to go a little deeper in terms of what basic skills you know, and you'll be required to write your own reaction and balance it. So for that reason, you should always have close to you when you're doing these problems. Obviously, a periodic table, you're going to need that for your molar masses. It is very helpful to have the reference table packet in front of you. If you have that, that will often contain your 5 main types of chemical reactions, so you can look at this and know how to predict your products. If you're a college student, you've probably memorized that. It helps to have a good knowledge of your polyatomic ions so that you can write chemical formulas, and also to possibly have an activity series in front of you. High school students, this will be in a reference table packet so that you can determine the products for single replacement reactions. Also a calculator you definitely need. So those are just some of the things you're going to want out. So most of those things I mentioned, you need just to do this first step, to write and balance your reaction. I also like to go ahead and find all of my molar masses so that when I'm ready for them, I need them. I'll point that out when we go through the problem. Now, here's how we actually do the problem. They're going to give you a given. They're going to give you a given amount of a substance, and that amount is either going to be in grams or moles. If it's already in moles, you're ready just to jump right into the mole to mole ratio. That's really easy, saves you some time. If the amount is in grams, which is really a more realistic way you would get it if you were working with it in a laboratory or industrial setting, then you're going to have to convert it to moles first. That is simply a gram to mole conversion, and we know that we go from gram to mole by dividing by the molar mass. Once you've got the given in moles, you are ready to multiply by the mole to mole ratio. This is actually kind of the meat of the problem. This is that new part that you're learning if you're just now learning this skill. And the mole to mole ratio comes from two things: what they gave you and what they want you to find. So what they gave you and what they want. And the numbers in the mole to mole ratio come from the coefficients in the balanced equation. Again, something else I will point out. When you plug that mole to mole ratio into your problem, just a little something to remember that might make your life easier. The moles of what you are given are always on the bottom, and the moles of what you're solving for are always on the top, because you're always going from what they gave you to what they're asking for. And then the last step is, if you need to, you can convert that answer that is in moles. If you were to stop right at the ratio, you can convert it to grams, or you might get lucky and have a problem where you are asked to solve for the amount in moles. So you just really have to pay attention to the unit that they are giving you in the problem and the unit that they are asking you to solve for. They may be the same or they may be different within the problem. So for a stoichiometry problem, I want you to think about it this way. Get the given in moles, if it's not already, multiply by the mole to mole ratio, and then make sure you got the right units at the end. And honestly, that's it. That's all there is to this. It's really pretty basic. So we're going to do 2 examples today. And we're going to go through the whole thing. We're going to write the formula. We're going to find our masses. We're going to balance the equation. We're going to cover all the stuff so you'll get a really good review. So what I would encourage you to do is go ahead and write this problem down, pause the video, and then we'll do it together. So the problem says, if 2.75 moles of zinc hydrogen carbonate decomposes, calculate the moles of carbon dioxide that will be produced. So honestly, the first thing I notice here is they gave me zinc hydrogen carbonate and they're asking me for moles of carbon dioxide. So I've kind of already just identified what they gave me and what they want. Now, we're going to go ahead and write this equation first thing so that we can look at it a little more closely. So zinc hydrogen carbonate is decomposing. Because this is a decomposition reaction, I know that I'm only going to have one substance on the left side of the arrow, and that is zinc hydrogen carbonate. So that's going to be Zn, and then in parentheses, HCO3, 2. I got this from crisscrossing zinc, which has a +2 charge, with hydrogen carbonate, which has a -1 charge. I know it's going to decompose. And if I look at my reference table packet, I'm going to look at the decomposition of metal hydrogen carbonates. And right here I see when a metal hydrogen carbonate decomposes, I'm going to crisscross that metal with carbonate. I'm going to add water and CO2. So if I crisscross the metal, which is zinc in this case, with carbonate, which is CO3 -2. Zinc is a +2, carbonate's a -2. The 2's will cancel each other out, and I get ZnCO3. And then again, the byproducts are water and carbon dioxide. So H2O and CO2. The order I write these in really does not matter. As long as I have these three things. If you had trouble writing that reaction, I have a YouTube video on writing decomposition reactions. Go through that. It'll teach you everything you need to know. Now, the next thing I'm going to do is I'm going to go ahead and figure up the masses of all these guys so that when I need them, I have them. So if I multiply the mass of oxygen by 6, the mass of carbon by 2, and the mass of hydrogen by 2, and I add those together and then add that to zinc, I'm just finding molar mass. I'm going to get 187.43 grams per mole. And honestly, this is just really scratch work for you. If you just write 187.43, it doesn't matter. I know the units are gram per mole, so I'm going to write that down. Zinc carbonate has a mass of, I'm going to calculate this up, that's going to be 16 times 3 plus carbon is 12.01 plus zinc, which is 65.39. And that's going to give me a mass of 125.40. Water, we know, has a mass of 18.02. And most people know carbon dioxide has a mass of 44.01. So what I've done so far is I just looked at what they gave me. They gave me zinc hydrogen carbonate. They're telling me it's decomposing. I write my formula for zinc hydrogen carbonate. I looked at the packet to make sure I knew what to do with that. The packet told me very clearly to crisscross the metal with carbonate, add water, and CO2. Now I'm ready to balance this reaction. So I'm going to do that in a different color pen just so you can very clearly see that work. I'm balancing this reaction because I have got to have the right coefficients in front of each of these formulas so that my mole to mole ratio is correct. So I've got zinc, hydrogen, carbon, and oxygen, zinc, hydrogen, carbon, and oxygen. So I'm taking an atom inventory. That just means I'm counting how many of each atom I have on each side. So I have 1 zinc, 2 times 1 is 2 hydrogens, 2 times 1 is 2 carbons, and 2 times 3 is 6 oxygens. I'm just multiplying across those parentheses. On the right, I have 1 zinc, I have 2 hydrogens, I have 2 carbons, because I have 1 here and 1 here. You add those together, that's 2. And I have 3, 4, 5, 6 oxygens. All right, so I'm going to go through and see what I need to change. Zincs are already good. Hydrogens are good. Carbons are good. And oxygens are good. What that means is this reaction is already balanced. We'll put a little check mark here. Sometimes you get lucky, and some of the ones that look really bad are very, very easy. So now we're ready to do our problem. So the first thing we're going to do is write down the given. And the given is 2.75 moles of zinc hydrogen carbonate. Go ahead and draw your line there. You might have to make it a little longer. If you do, that's fine. So I've written down my given. And what I notice is the given is already in moles. That has saved me a step. I'm not going to have to do a gram mole conversion because I'm already there. Because this given is already in moles, I have permission to multiply by the mole to mole ratio. Now, the mole to mole ratio is between two things, what they gave me and what they want. They gave me zinc hydrogen carbonate, and they want me to solve for carbon dioxide. This is what they gave me and what they want. Now, we don't write ones when they're coefficients, but technically all of these were ones. So that means there is a 1-to-1 ratio, I get that right here, between zinc hydrogen carbonate and carbon dioxide. So these two guys make up my mole-to-mole ratio, what they gave me and what they want. What they gave me is going to go on the bottom. What they want is going to go on top. So they gave me 1 mole of zinc hydrogen carbonate. They want carbon dioxide. I have 1 mole of carbon dioxide. Now I'm just writing those ones in red because I'm really wanting to emphasize this mole to mole ratio, because this is what stoichiometry is. It's just all about that mole to mole ratio. You're comparing one thing to another. These just both happen to be ones. Now, what I always tell my students is anytime you're going from gram to mole or mole to atom, mole's just an understood one. Don't write the 1 in front of it. And I say that because in the mole to mole ratio, always write the numbers even if they are ones, because that to me makes this really stand out as the mole to mole ratio, which is a very important step. So I wrote down my given. It was already in moles. I had permission to multiply by the mole to mole ratio. I found my mole to mole ratio, what they gave me and what they want. It was a 1-to-1. I plugged it in. I knew to put the 1 mole of zinc hydrogen carbonate on the bottom because it was on the top in the previous step. Remember, in dimensional analysis or factor label, whatever you want to call this little method, whatever's on top is always on the bottom in the next step. Now, what did they ask me for the answer in? Did they want moles, grams? I look up here and it says calculate the moles of carbon dioxide. They specifically wanted me to give this answer in moles. And what that means is I'm done. I'm ready to calculate this and be finished. Because if I stop right here, my answer is going to be in moles of CO2. So that said, I would multiply everything on the top together. 2.75 times 1 is 1. Divided by 1 is 2.75. So the answer is 2.75 moles of carbon dioxide. I just figured out that if I have 2.75 moles of zinc hydrogen carbonate and it decomposes, I am going to also make 2.75 moles of carbon dioxide. And that makes sense because they are a 1-to-1 ratio. So that would be a really simple stoichiometry problem where they give you moles and ask for moles. It's always going to be really short. Now, we don't always get that lucky. Sometimes we have to do a gram conversion, possibly on the front or the back end. So we're going to take a look at one of those next. So go ahead and take a moment to pause your video and write this problem down. You might even want to try to go ahead and write the reaction and balance it, see if you can get that correct, and then we'll go ahead and jump into this problem. So this problem says excess lead 2 nitrate and 1.3 moles of potassium iodide react in a beaker. Calculate the masses of each product formed. So they gave me the amount of potassium iodide. When they tell me excess lead 2 nitrate, that just means you don't need to worry about it. There is plenty of it. What they're really telling you is this is what you're going to run out of first. You only have 1.3 moles of potassium iodide, but you've got plenty of the lead 2 nitrate, so that's not a concern. Now, what I can see is I am putting lead 2 nitrate, which is an ionic compound, with potassium iodide, which is also an ionic compound. That means that what I have here is a double displacement reaction. So we're just going to go ahead and write down the lead 2 nitrate, which is PbNO3 2. I got that from crisscrossing lead with a +2 charge with nitrate, which had a -1, plus potassium iodide. Potassium is K + 1, iodide is I - 1, so that is Ki. Now, anytime I have a double displacement reaction, 2 ionic compounds, what's going to happen is they're going to switch partners. And the easy way to remember this is you're going to put the outer 2 together, and then you're going to put the inner 2 together. Remember, you have to have a positive with a negative so that the charges cancel out. So if I put lead 2, that would be Pb with a +2 charge, with iodide that has a -1 charge. That's going to be PbI2. Plus, now I'm going to put potassium with nitrate. Notice I said potassium first because we always write the positive one first. So K has a +1 charge, nitrate has a -1 charge. They're going to cancel, so that's going to be KNO3. Now, before I balance this, I'm going to go ahead and figure out all of my masses and jot those down. Again, that's not a necessary step, but I do think this is something very helpful, especially for beginning students. So the mass of lead 2 nitrate, I've already figured that up, is 331.22 grams per mole. Just added all these masses together. The mass of potassium iodide is 166 grams per mole. The mass of lead 2 iodide is 461.0 grams per mole. And the mass of potassium nitrate is 101.11 grams per mole. So now that I've got that done, I'm going to balance this so I can have the correct coefficients for my mole-to-mole ratio. So we're going to divide this in half and take an atom inventory. I have lead, nitrogen, oxygen, potassium, and iodine. I'm going to repeat that list on the other side. Lead, nitrogen, oxygen, potassium, and iodine. I have 1 lead, 2 times an understood 1 is 2 nitrogens. 2 times 3 is 6 oxygens. I'm just multiplying across the parentheses there. 1 potassium and 1 iodine. On this side, I have 1 lead, 2 iodines, 1 potassium, 1 nitrogen, and 3 oxygens. So now I've got to get this thing balanced. That means I've got to put the correct coefficients in the front. I'm taking educated guesses, so I have the correct mole-to-mole ratio. Leads look good. I'm not going to mess with those. Nitrogens, I've got 2 over here and only 1 here, so it makes sense to maybe try a 2 right there. Now, sometimes your guess is not right, and if it's not, just mark it out and try something else. But I think a 2 looks pretty good. 2 times 1 is 2 potassiums, 2 times 1 is 2 nitrogens, and 2 times 3 is 6 oxygens. Notice this is a little review for you, but when you put a coefficient in front, you have to change every single atom in that formula that follows, and I usually just work through methodically from left to right. So my leads are good, my nitrogens are good, my oxygens are good. I've got 2 potassiums and 2 iodines here and 1 of each here. That is a really easy fix. I'm just going to throw a 2 in front. That gives me 2 potassiums and 2 iodines. I now have a balanced equation. So I've got any ratio I could want here. For example, there's 1 lead nitrate to 2 potassium iodides. There's 1 lead 2 nitrate to 2 potassium nitrates. There's 1 of these to 2 of these, and so on and so forth. But really what I'm interested in is what they gave me and what they want. So let's take a look at that real quick. They gave me the potassium iodide. So this is the one they gave me. And they want me to calculate the mass of each product formed. Now, when they say each product, I've got 2 products. That means I'm going to calculate the mass in grams of how much of this I made, and then I'm going to do a second problem and calculate how much of this I made. And when they say calculate the masses, generally, unless they state otherwise, that means they're looking for grams. So this time I'm going to have 2 different ratios I'm working with. I'm going to work with a ratio between these 2, which is a 2 to 1. And then I'm going to work with a ratio between these 2, which is a 2 to 2. So we're going to start with this. We're going to solve for the lead 2 iodide first. So this is the first one I'm going for. We always start with the given. And so the given in this case was 1.3 moles of potassium iodide. Now the good news here is the given is already in moles, so that means I have permission to jump straight into the mole-to-mole ratio. And this first mole-to-mole ratio is going to be between potassium iodide and lead 2 iodide because this is the first one I'm solving for. It's a 2 to 1 ratio, what they gave me to what they want. So on the bottom, I'm going to have the 2 moles of potassium iodide to 1 mole, because that's an understood 1 mole of lead 2 iodide. Now, if I stop right here, my answer is going to be in moles, but they specifically said in grams. So real quick, I'm just going to do a mole to gram conversion. A mole of lead 2 iodide has a mass of 461. So 461 grams of lead 2 iodide per mole. Now, just to walk you back through, when we started off with our given, as soon as we hit this ratio, the ratio is where you switch substances. So suddenly I'm done with potassium iodide and I'm working with lead 2 iodide. And then this is just a little housekeeping on the end. They said, no, I don't want the answer in moles. Give it to me in grams. And we know very quickly how to go from mole to gram. So we're going to calculate this first. And what we're going to do is we're going to multiply 1.3 by 461. You can either write that down or just hit equals. Make sure you hit equals. And then divide by 2. So 1.3 times 461, hit equals, divide by 2 is 299.65 grams of lead 2 iodide. So I just figured out how much of the first product I can make. Now, you didn't have to do this one first. You could do the other one first. As long as you do them both, it doesn't matter. All right. Now we're ready to use the same information and say, okay, if I have 1.3 moles of potassium iodide, how many grams of potassium nitrate can I make? So we're still going to start with the 1.3 moles of Ki. It's already in moles, so I'm ready to jump right into my ratio. The question is, what's the ratio between this time? And the answer is, I'm starting with this and I'm solving for this. This is a 2-to-2 ratio. I have 2 moles of potassium iodide to every 2 moles of potassium nitrate. What they gave you, those moles are always on the bottom. So 2 moles of Ki going to what they want, which is 2 moles of KNO3. They did ask for the answer in grams, so I'm just going to quickly convert potassium nitrate to grams. Potassium nitrate has a mass of 101.11. So looking back through my problem, these moles canceled. I switched substances right here, and then we went from mole to gram. So if I multiply 1.3 times 101.11 and divide by 2, I'm going to get 131.44 grams of potassium nitrate. So the reason I chose this problem for the video is you just have to be really careful about paying attention to what they give you and exactly what they are asking for. You know, when they said each product, they are expecting you to know, the person who wrote this problem at this point is expecting you to know that this is double displacement, so you're going to have 2 products. And when they say each product, that means you're going to have 2 answers. But what you notice is we used the same given, and we just did 2 separate problems. We did one comparing these to find this mass of lead-2 iodide. Then we did a second problem comparing these to find the mass of potassium nitrate. This problem could have very easily just said, calculate the mass of this or this. It could have said, calculate the moles of this or this. And in those cases, your work would have looked a little shorter, a little different. They're all very small, simple steps. You just got to put them together in the correct order. And again, the very last thing I want to point out today is this mole-to-mole ratio, the heart of the problem right here. You notice this is the only place where I actually write down a number in front of the word mole. Obviously, if the given's in moles, we would put a number with it. But anytime you're doing a mole to gram conversion, you just write the word mole, and that makes it really easy to remember. So you've seen a very easy, very short stoichiometry problem today. You've seen one that involved a few more details, but in the end, the heart of the problem remains the same. It's all about that mole-to-mole ratio.